Start the video whenever you like.
So this is our lab. It's about the force of lift on an airplane wing and how it relates to an angle of attack. Yeah. And so the angle of attack can actually be defined. It's like the angle that, so if it's horizontal and the wing is up like this, then this is the angle of attack right there, theta. So, I guess you want to explain how that works?
So this is a diagram of our tunnel. So we have a propeller down here which sucks the air down on the wing. We have two rods that hold the wing up and then that's the wing in the middle. We also have some straws here to streamline the wing.
Alright, and then how a wing actually works is there's more like kind of 3D area on top, which makes the density of the air and I guess the pressure less at the top of the wing. And since this thing wants to go to lower energy, it gets a net force up. So that's pretty cool too.
Also, the reason the angle of attack matters is because of the normal force on the surface.
Yeah. And so these are our materials we used. We used like I had an old model airplane, a lot of those parts, so I just tore that apart. And then we used like a model airplane wing, all the same wing. We just cut it into little sections that have the same area. And so really what we're analyzing here is sort of the equation of lift. So it's kind of this equation that's derived from Bernoulli's principles. And there's no theta in the equation, but theta is defined in the C, which is the constant of lift, or coefficient of lift. But it's not really constant as one may think, because if you guys remember that lab where we dropped coffee filters, that was just like a coefficient of drag, which is like the coefficient of lift, but it changes per velocity and per area, and per like wing type as well. So, not constant at all. Oh, did we go into far? No.
So yeah, this is just explaining the how it works again. So here we have the propeller here sucks the wind that way, and the wing to kick up, and then the wing
Oh yeah.
So the propeller sucks the wind through, and here's the wind. So what we did is we put a force sensor below it. We put it up on some chairs. We put a force sensor below it. And so we got readings. We use that.
And then we also we revved the throttle up to full throttle like that, and we took video analysis of how fast it accelerated upward. But in video analysis, you have the friction of the rod against the straw. So we actually use that as our error analysis when we compared it to just the force sensor.
So this is just a couple pictures of us building it. Here's our David's first diagram of it, and then just through the we first started off with the two ends, and then putting the plexiglass part on, and then connecting them. And then we did a couple of tests with just some cardboard before we started doing all the stuff.
And so this is the initial graph. It shows coefficient of lift against angle of attack. And even though it's not the force of lift, the coefficient of lift is related, and then it's in the equation for the force of lift. So if it were force of lift against angle of attack, this graph would just be scaled way up, because it'd just be multiplied by a bunch of other things. And based on this graph, it peaks at about 17.5 degrees. So we thought that our angle of attack would be about 17.5 degrees, the angle of attack that would produce the most force of lift.
Are these published data or your data?
That's published.
Okay, okay.
So this is our procedure. We built the wind tunnel, and then we just go through how we put it together, what our thoughts were, and then so we did it two ways. We used a force sensor and video analysis. We knew the video analysis wasn't going to work as well because of the friction on the rods.
So we did 3 trials per wing section of getting video analysis, and we can get the acceleration from that, take an average, and then we calculate the net force of lift on that wing. And then to all the readings on the force sensor and taken in video analysis, we added the weight of the wing, because that would give us the total force of lift that was being exerted. And this is our data table. It's kind of smushed on here. I have a link to it, but it looks better in Google Docs. It just, oh, are you gonna go? No. It just shows our 3 accelerations we measured and the force sensor, as well as the weight of the wing, and calculations for that as well.
So these are 2 graphs using video analysis and a force sensor. And as you can see, our peak was about 0.11 newtons for video analysis and like 0.17 newtons using the force sensor. So somewhere in there we lost quite a bit of force, and that was due to the friction.
Alright, and so there was some sources of error in this lab. The wind speed in the tunnel couldn't possibly be completely constant. We used a thing called a tachometer, which measures things, how many times they go around spinning. Oh, I guess the propeller's over here. So we pointed the tachometer at the propeller and made sure it was nearly constant, because if the propeller's going around at the same rate, then the wind speed should be the same per trial as well. So that should be good for that. And these are our actual error calculations when comparing. We called the force sensor value our accepted value and compared it to our video analysis. And so it shows the video analysis had a 63% error, which I guess makes sense because of the friction.
So we ended up finding that the 30-degree wing had the highest force of lift, the greatest force of lift, and we think that it's just because each wing has a different maximum optimal degree angle of attack, and so
Yeah, and that like the angle, the max angle of attack that produces the greatest force of lift varies per airfoil type, and airfoil is just what the material is. So I guess for this type of foam, it would be about 30 degrees.
Great, let's thank our presenters. Taking some questions?
No questions?
You said that it was the type of material used. Did you mean the shape of material used?
The shape and the type.
The type also?
Yes.
You mean the outside of it? Because I can't imagine that the inside of it would affect
yeah,
it.
because I guess it'd have a different coefficient of friction
Sure.
per different type.
What was the range of the angles that you tried?
We tried 5 to 35.
5 degree increments.
Yeah.
We also had a 17.5 degree accelerator.
Yeah, right, that's true.
Yeah.
Any more questions?
What kind of airspeed did you get out of your wind tunnel?
We have no idea. We didn't have an anemometer, so that measures wind speed, but I think like 10 or 15 miles an hour at the most.
Yeah, like, it's not really important that you know like how much it is. You just need to know that it's constant,
Yeah.
and it was. So.
Yeah, that's the important thing.
Cool. Thank you, gentlemen.